Okay, in the first part of this we were looking for all sorts of details. Now we're looking at routing information. We filtered on RIP and we're attempting to find out what we can see. So let's look at the basics. For a start, we can see that the source of routing is 172.30.250.254. This must be the address of the router. We can see that it is sending the traffic to 250.255, the broadcast address within this subnet. We can see we're running RIP version 2. RIP sits on an Ethernet 2 frame. Its destination is not to a known MAC address but to broadcast, and its source is from itself from a 3COM network card address. Ethernet 2. In IP, we can see the IP addresses in a little bit more detailed. We have no differentiated services field. We have no flags. Our time to live is 64. 64 hasn't changed. 64 is constant, or is a power 2, therefore it is inside the subnet. It hasn't crossed the subnet. Our header checksums are okay. Let's minimize those two. Let's have a look at our UDP. Source port 520, destination port 520, both UDP, indicates RIP version 2. Let's open up RIP. We can see that we're in response 2, RIP version 2, domain 0. Let's have a look at all these numbers down here. We have a network 0000, which is apparently being advertised by RIP. We have a network 192.168.1.0 advertised by RIP. We have a network 192.168.250.0. Okay. We have a network 172.30.251.0. Okay. Now 172.30 is a class B, or a 16-bit mask. However, we will look and find that our masks are 255, 255, 255. So we can see that we are using classless routing. We also have a network 172.30.252, again classless routing, and 172.30.253, classless routing. So we can see a great deal published from this network. We remember that RIP itself always broadcasts the entire routing table, which is what has happened here. So we now know that we have, we know from previously that we had a switch, it was 3COM. We now know that we have a router. Okay, so we've done quite a lot of analysis with this. I wonder if there's anything we've missed. You never know if we missed something, you can never tell. Statistics, protocol hierarchy. We now have a little graph here, or table, showing us how the protocols are stacked up. Everything is Ethernet, most is IP, some will be ARP of course. TCP. Inside TCP we had NetBIOS session service, SMB and data. We had HTTP. FTP. There's 0.26% FTP. We didn't notice that before, so we're going to have to go and have a look at that in a moment. We had UDP, we had DNS, domain name service, RIP, routing information, and Bootstrap. We've already had a look at Bootstrap. We know that we had DHCP assigned to here. We've had a look at ICMP, ping messages if you recall, right at the very beginning. And we've seen LLC data, spanning tree protocol, and we've seen ARP. So the only thing we've actually missed out of here is FTP. So let's go and have a look and see what we can find. I'm going to do a display filter on TCP, on TCP port 21 called FTP. Let's have a look what we found. Okay, I found a particular frame. I can go through each of these frames in turn, or I can follow the sequence. So instead of having that display filter, I'm going to follow the TCP stream. Okay, it's rewritten the filter, and this is what we have found. Here we go. We now know that we are running FileZilla server. Okay, it's written into the banner. That's enumeration. You can also see a quote there that someone's added. This is the lab exam. Tom Baker is the best doctor. Okay, so there's obviously a quote that you were meant to find. The username. I'm attempting to log in with the username forensic. Password required for forensic, James. Okay. We then see some port information, we see the list command, we see nothing returning, and we see goodbye. So we have found some information there. We've got usernames and passwords and type of server. I wonder where FileZilla server actually runs. Let's go to our good friend Google. FileZilla. Oh, my mistake. FileZilla, the free FTP solution. Okay. We now find FileZilla server Windows only. Excellent. So we now know that that must be running on a Windows based system. Close that. We now know that 172.32.52 must be running some form of Windows. Okay? And one was talking to it. That's quite handy. Let's see if we can find any other instances of FTP. You never know, there might have been more than one. We have 172.32.52 talking to one, and there's another IP address here, 172.32.53.100. I'm going to filter on that session. Okay. FileZilla server, it's the same software. Stargate Atlantis has been cancelled. Another quote for you to find. User forensics. I wonder how many people will notice that the user was forensic, and in this case the user is forensics. Password James. Okay. Again, no files listed, and the system has closed. We have found out something useful there. That's quite handy. I'm just going to look for some arbitrary port numbers now, and I'm going to do so by creating my own display filter. You can go to the menus, or you can pick up the syntax. TCP.port equivalent to 2222. Nothing there. 2222 is often a port that's used by some people. Port 222. Port 222 is in use. Port 222 is often a redirected SSH port. I'm not sure if that's the case inside here, but it certainly seems like something was actually going on here. We have very little data. We only have 2 frames. We can't really tell a great deal from that. Well, the only thing left to do now is to get some ballpark statistics. Let's have a look at the summary. We can see how many frames were transmitted, how many frames were received, what the bytes were inside here. Let's have a look at the input-output graphs. We can see that this capture lasted for, well, from 0 seconds, a big pulse of data, and then it went up to about 165 seconds or something like that. So you can see that how long this capture actually went for. There are other kinds of analysis inside here, like Ethernet. One thing I am going to have a look at, if we can, is, where is it? Where has it gone? Flow graphs. These sort of flow graphs are very useful when you've got a particular TCP stream where you can see the command or the bidirectional data flow between different systems. We can see NetBIOS name service here, NBSS, and we can see readx from SMB. And there's an awful lot of frames here. As you can see, some of them are going between different endpoints. These are all the endpoints noted on the top. So we don't exactly know where they're going or what they're doing, but at least we can see that something is happening inside there. TCP graphs, not particularly useful. Let's find a TCP session. Okay, we found some TCP. I'm going to follow that stream. Okay, this was obviously some sort of HTML. There's not a lot there, not many frames there. Let's find something a little bit bigger. Let's find a bigger HTTP stream, one where we're downloading a lot of data. Again, not many in our TCP session. We ideally could want a little bit more. Let's see if this is enough to do a TCP round trip time graph. No, we haven't got enough data there. What about TCP throughput graph? Here we can see time running in this axis, and we can see the amount of bytes per second coming back. Here we have some elements and then some further elements. As you see, we've only got several dots here because we only have a relatively small session, a more small sequence. Let's see if we can find a really big TCP session. We've got quite a lot of data there. Let's again do our TCP throughput graph. Excellent. What we can now see here, all these dots are as we are exchanging data. Okay, we obviously have some sort of like peak data rate at the top, and we fall off once we've actually gathered. Let's think about HTTP. HTTP, if it's 1.1 version, will be in parallel, so all graphics will be transferred simultaneously. That may account for why we've got such a large throughput here, and they all seem to tail off. Once all the graphics are downloaded, they will tail off, and then we're down to a relatively low level down the bottom. Certainly does explain what's going on. Again, this axis is effectively time in seconds. This is about 15 seconds worth of download. So this could be a complex web page being downloaded and displayed. If you think of Kylie.com as a web service, once you're logged in there may be a lot of pictures, graphics, or even audio content being downloaded at the same time. So as you can see, I've walked you around many of the facilities inside the Wireshark. We've analysed data in a considerably good, in a reasonable way, and you should have had a particularly good way of checking the data. Google's always going to be your friend whenever you do anything like this, because you can quite easily analyse a data stream and see what's inside it. That's it for this